Okay. First, I would like to thank the organizers for the kind invitation. It's my great honor to be here to give this talk. But today I will talk about some very simple idea to construct the so-called multi-fidelity surrogate model for Bayesian inverse problems. This is the joint work with my collaborator Yan Liang from Southeast University. This doesn't work now. Okay, this is the outline of my talk, and first I will give you some very basic introduction for Bayesian inverse problems, and then the surrogate model-based acceleration for Bayesian inference, and the main part is the third part for the multi-fidelity approach for this problem. And let's begin with this very general inverse problem. Here the M is the input random parameter, not random, it's input parameter which you want to recover. And D is the data, observed data. Maybe noise, maybe it's with noise data, and the G is just the general forward operator. And this is the general framework for the inverse problems. The one method to solve this problem is the so-called regularization problem. So you can choose a kind of regularization to solve this optimization problem. The key issue is how to choose this kind of regularization and how to solve this optimization problem in an efficient way. And this kind of methods where you add a single value of the recovery parameter n, but it's very hard to quantify the uncertainty of the parameter or the confidence level of a parameter. So another approach is the so-called statistical approach, where you model the input parameter as a random variable. Then you can use the Bayesian rule to find the posterior of the random parameter. But here you have to give prior for the input parameter. And then you use the Bayesian rule to derive the posterior of the parameter. And in this method, you can quantify the uncertainty of the input parameter actually. But here, the full model will go through this likelihood function, which when you solve this problem, you will also need to solve the full model for many times. So the main tool for this Bayesian problems is the MCMC approach, where you just sampling directly from the posterior. Here and then again, in this sampling procedure, you have to solve a lot of forward model, the full model. And to actually, this kind of approach can be very useful, but still there are many challenges for this approach. And these are the main challenges. So to speed up this kind of approach, and you can consider two kind of things. The first one is to develop a new efficient alternatives to the MCMC. But this talk, I just gave you some basic idea for the surrogate model and a method to speed up this kind of approach. That is, we can build a very cheap surrogate model to the full model, and then use this with MCMC to speed up the computational procedure. So the idea is very easy, and you build a surrogate model for the full forward model. Then you can perform the Bayesian rule with this surrogate model. It's very simple, and this kind of a surrogate can be built in an offline manner. and no additional forward model solver will be needed for the online computation. And consequently, you can sampling the posterior with very large number of samples. What about the convergence of this kind of problems? Actually, there are a lot of convergence analysis for this kind of approach. It just says that the KL divergence between these two measures, the true posterior and the computed posteriors, can be bounded by the error of the sangee model. But this error is measured in the prior measure space. So if the prior is far away from the posteriors, these kind of terms are not necessarily very small. So, but most of the analysis is based on the prior space. There are different setting and different prior and different results, but similar results for the bounded of this kind of error. But how to build the sangee model? There are a lot of ways to build this kind of sangee model. A lot of methods can be used. So here I just presented the idea with polynomial chaos approximation. But you can also do Gaussian process or even deep learning. This is kind of offline computation to build a sangee model for the forward problem. So I just presented the idea by using polynomial chaos, which is very simple and very easy to present. And we also have some results on Gaussian process sangee model. So the idea is just to expand the parameters with polynomials, which is very popular if the map is in some sense smooth with respect to the parameter. So you can use certain kind of polynomials to approximate the map to get a sangee model. And then by using polynomials to approximate the model, you can do a Gaussian approach or collocation approach. A lot of results on this kind of methods, and I will not go to details for this kind of methods. Just keep in mind that we can use this kind of method to build a sangee model for the full forward model. And then combine this sangee model with MCMC can be very efficient because you don't need to compute the full model for the online computation. But what about the accuracy? As I told you before, if the prior is far away from the posteriors, the accuracy of this kind of problems is not guaranteed actually. Let me show you a very simple example. The goal is to recover this field in here the coefficient. This is a 9-dimensional problems. The unknown is the coefficients of this field expansion here. This is the prior of these parameters, and the true weight is drawn randomly by this measure. And this is the true field actually. And consider if you use this kind of sangee model, if you use the full model, meaning that when you do the MCMC, you always solve the full forward model. Then the computational time is this quantity. But if you use a PC-based, polynomial chaos-based sangee model, this can be very efficient. This is high-order polynomial chaos expansion. This is low-order polynomial chaos expansion. But actually, with high-order approximation, you can see something like the true field, but it's not with very large error actually. But the computation time is already very big here. So the main reason is the big difference between the prior and the posteriors. So this is a CPU time for the online and offline computation. Because for PC-based approach, you need some offline CPU time, but online you just solve the sangee model, so which is very cheap. But to solve these problems in a better way, actually, why we consider the multi-fidelity approach, meaning that besides the polynomial chaos surrogate, you can also include some forward model simulations to combine this kind of two-fidelity approach to give a better approximation. So this is the idea, very popular idea in UQ study and a lot of results. And this is the recent review on this kind of approach for different problems. So our idea for doing this kind of multi-fidelity approach is like this. You have a surrogate model here, but we just compute in some points in the correction term. As it's not that necessary, this surrogate model is very accuracy for the forward model in certain points. Then you can consider a correction term. And this term is again approximated by polynomials. And then if you can, online you can do this in an adaptive way to construct this kind of correction term, then you can actually again very good accuracy compared to the only one fidelity PC based from surrogate model. This is the simple idea actually. If you combine this idea with MCMC, but this is the standard MCMC approach. But the difference is just after a few sampling procedures, you just stop and to compute the difference at this sample, at this fixed sample, to show whether you need to refine your surrogate model. If the error is large, then you can update the surrogate model by adding some correction term there. But in this step, actually, you have to solve a few forward model simulations. This is more detailed. So after a few sampling procedure, you can stop with these points, these particular points. And if around this point the error is very big, this is the true forward model, I think. I use high fidelity, meaning that this is the true forward model. If the error is big, then we can sample locally around these points, and to build a correction term and add this term to the surrogate model to compute a new surrogate model, and then proceed this MCMC rule, and then again to do an iteration. So this is the error bounds of this new multi-fidelity approach. This difference is bounded by these two terms. This is the tolerance. You measure the error, whether you want to update your surrogate. And the other term is given by the posterior measure, but with respect to the posterior measures, different from the previous work. But this term is something like, it's hard to quantify how big it is. This term is depend on your method, depend on the computational details, but it's essentially it still can be controlled by this tolerance. But if you set a very small tolerance, meaning that you will need much more forward model simulations. So there's a balance between the tolerance and this kind of accuracy. Anyway, this is just the error bounds of the methods, not fully convergence analysis, because it's very hard to quantify this one. Actually, it's adaptive procedure. Again, let's say the similar results for the similar example, and then now we use the adaptive multi-fidelity surrogate model. Then you can see that if you use only with order, polynomial order is only 4, then you can get a very accuracy results with less CPU time compared to the previous results. Because in the previous case, for polynomial chaos surrogate with n equal to 7, the CPU time is much bigger than this quantity, actually. But here actually we have performed a few forward model simulations, but still it gains a lot of speed up compared to the single fidelity PC surrogate model. But you can even do this with very low polynomial order. But this is the CPU time, and actually you can see that for this kind of surrogate model, we have performed more or less 600 forward model simulations. And for this one, we need 1,000. But this is the full forward model simulation based on the full forward model. You need a lot of forward model simulations. And this is the PC-based surrogate model. You don't need to do the forward model simulation, but you do have offline computations. This is a total time for the computational procedure. You can see for this example, and the approach works very well. And if you further reduce the tolerance, actually this number will be increased for sure. And this is another example. The purpose is to inverse the source of this equation. It's a two-dimensional example. The prior is uniformly on this domain. And you can see that this is the present, this is the picture to show you how the method works. Left-hand side is the prior-based surrogate model, meaning that you just construct the PC surrogate model based on the prior information. Then you have to construct the polynomial chaos expansion. Here we use some least squares to solve the annual coefficients. But this is the points you sampled in the whole domain. And this region is the true posterior region, actually. So the posterior is concentrated to this region, actually. You can see that most of the points are far from this region. That's why the surrogate model actually doesn't work very well. But here, this is the multi-fidelity approach for different iterations. So the right one is the first iteration. After the first iteration, we always sampling in a local bar with MCMC approach. So after a few iterations, most of the points where goes into this region here, so that the surrogate model will be very accurate compared to this truly prior-based, one fidelity PC-based surrogate model. So this is the reason why this problem works very well. We always choose points near the region in the posterior region. So this kind of points will be very useful. And this is the approximation results. You can approximate the distribution function, actually. This is for the single fidelity polynomial chaos surrogate. And you can see that even with very high order polynomials, you can't find a good approximation. But if you do this with a multi-fidelity approach, even with very low polynomial order, you can get a very good match between the numerical solution and the true solution. And actually, this is the basic idea to do the adaptive computation for inverse problems. And the idea can be essentially extended to the ensemble combined filter approximation for inverse problems. The ENKF is also very popular for inverse problems since this paper. So the idea can be also combine this idea with ENKF. Just so you also, we introduce the surrogate model here. And we will add a step to update the surrogate model. So this can be very efficient. And this is another example using ENKF This the purpose is also to recover this field here. It's a 9-dimensional problems, unknown the 9-dimensional parameters, and this is the true field. And with a polynomial-based single fidelity approach, actually, you can find that you can't get a good approximation for the true field, even with very high polynomial order. This is a 9-dimensional problem, so this kind of order is very high actually. You have to use a lot of modes to approximate the field. But if you do the multi-fidelity approach, actually you can do it even with 2-degree polynomial space. And with very fast computation, you can get similar results with the true field. So the method can be very powerful actually. And also actually the iteration time and also this kind of CPU time is very robust to the sample size actually. The sample size increase and the method seems to be very stable. And the iteration steps will not increase very much. So that's all what I want to say. And this is the 2 references on these problems. And we want to extend this kind of ideas to different sangee model and to combine this idea with other reduced order modeling problems. So thank you very much. For Gaussian process sangee, we also have some previous results on the simulations. And for Gaussian process, we also to compute the error and then add 1 point at one step and at 1 point, something like that. The
difference in terms of
performance is very good, I think, but I should say that the performance looks very good is only for this kind of problems. Maybe for some problems, I don't know, maybe, but because the error analysis is not true analysis, we can't quantify the term there. So I guess for very hard problems or even very high problems, maybe there's also other problems. We have to combine with other model reduction problems. But for Gaussian process, for sure we can do the same simulation and same results.